Welcome to Data Saturday 1, which is the second Data Saturday chronologically, but the first one in our hearts. Glad to be able to present for this group, and thank you to all the sponsors who've made this possible. Our session is called Classification with Naive Bayes. Now I'm going to switch back to the slides that I'm going to use, but I did want to call out the sponsors and say thank you to everybody who's helped put this together, especially in the wake of what has happened with SQL Saturday. And we'll see what happens in the future with SQL Saturday. But for today, let's talk about some data science stuff. So my name is Kevin Fiesel. I run a predictive analytics team here in Durham, North Carolina. I'm a Microsoft Data Platform MVP, and I have a blog called Curated SQL. The idea of Curated SQL is that I would like to try to find and link to 5 to 10 interesting posts per day on topics like database administration and development, R, Python, Power BI, Scala, Hadoop, Spark, anything in this broad data platform space. So that's curatedsql.com. Let's talk about this naive Bayes approach. And by starting out with what is naive Bayes? Well, it is generally called an algorithm. There's the naive Bayes approach. Technically, it's a class of algorithms. There are quite a few variants on naive Bayes, but for the purposes of discussion today, I'll probably still refer to it in the singular. If I say naive Bayes is, please note that I really mean the whole class of naive Bayes algorithms. This is a really good concept for developers to know and for data scientists to know because it's quite easy to understand. It's reasonably accurate, does a pretty good job of things. So when you're working on a classification project, this is a great starting point. This is what I would call a, say, first step model. And by that, I mean, you use naive Bayes because it's fast, gives you some reasonable results, and is easy to understand. And if your results are good enough, you can feel confident that you're going to have a good solution to the problem. You can then change to other algorithms, try other approaches to get better. But if naive Bayes is doing well, it's a really good sign. If it does poorly, it's not necessarily the end of the world, but it may be an indicator that you might not have the right data or you might not have the right problem. So it's a good indicator that gives you an answer fast. Naive Bayes algorithms are going to follow a general form. They are all probabilistic. So we calculate the probability that this thing belongs in this category, and we try it for each of those categories, and we find out which one has the highest probability and say, you belong there. These probabilities are derived from a calculation known as Baze's theorem, and we'll talk about that in a little bit. The features are considered independent. So let me talk about what I mean by a couple of terms. First, I mentioned classification a couple of times. The idea of a classification problem is I have, for example, a newspaper article, and based on the text of the article, it might end up in one of several sections of the newspaper: the sports section, the business section, the weather section. I want to be able to read that text, analyze the words in that text, and apply it to the right section. So to do that, I'm going to have some features about this newspaper article. Perhaps I have things like the number of words. I might have the number of paragraphs. I might have the author. And based on those sorts of inputs, I'm going to say, well, if the author is this and the number of words is within this range, then it's probably a sports article. Independence here means that we expect that the name of the author and the number of words and the number of paragraphs will all be separate from each other, that there's no correlation, there's no nothing that works like these authors only write these size of articles and these other authors only write these long form articles. So these features are considered to be completely separate from each other. That's why this is called a naive approach, because in reality, certain authors are told to write articles of certain lengths. And so there is some covariance. things move in the same direction based on this author, based on this length of article. And so it's not truly independent, but once you add in these dependencies, it gets a lot harder to understand. So we start off with the naive approach, the independent approach, and work from there. Today's talk, I'm going to show you how this class of algorithms works. We're going to start off with some really easy forms of it, and then use R packages to try out a couple of larger scale problems. There are more forms that we're not going to cover. There's a lot of variation within this class of algorithms, but I think we're going to get enough of the basics that you'll be able to walk out of this knowing how it works and how you can implement. And by the way, if you live in the .NET world, you're a .NET developer, you can easily use naive Bayes in .NET code as well. So our agenda here. Excuse me. We will first solve for naive Bayes. By the way, there is math in this, but not too much math. It won't be too bad. Bayes' theorem, if you remember from a statistics class that perhaps you've tried to forget over the years, is in the shape that we see above. So the first element, which is the probability of B given A, and let me draw a couple boxes here. So the probability of B given A, which is how you read this thing, it's also called the posterior probability. So what this says is the probability of B might be that this is a weather article, and A is the data that we have. Here's the author, here's the number of paragraphs, here's the number of words. So this calculation is the same as the probability of knowing that this is a weather article. So given that this is a weather article, expecting the probability that the author will be X, that the number of paragraphs will be Y, that the number of words will be Z, multiplied by how frequently we get weather articles, divided by how frequently we get articles from this author in this word count with this number of paragraphs. So this thing, P of B, is also known as the prior probability. That's just the likelihood that the hypothesis will be true. That is our expectation of how likely this will happen. To give you an idea of solving this part is actually really easy to do. This part is nearly impossible to do in practice. So what we do is we approach the solution. And let's talk a little bit about that. I also want to point out that I mentioned the case of 3 inputs: author name, number of paragraphs, number of words. Well, remember, this is independent. So what that means is we don't really have where A is the whole set of data. We don't have to think of it as all of the data points. We can instead think of it as, what is the probability, given that this is a weather article, that Bob wrote the article? What is the probability, given that this is a weather article, that it's within 300 words? What is the probability that, given a weather article, it is 5 paragraphs? And then we multiply by, what is the probability that this is a weather article? So these terms are independent. We don't have to think about how X1 and X2 operate. We don't have to think about X2 and X3, X3, X4, X1, X2, X3. We don't have to think about all of those complexities. We purposefully ignore them. Hence the term independent. Okay, that was the statistics primer. Try to wake up the mind and remember what all this stuff meant. Now let's try to solve a problem using this algorithm. So I want to figure out if my boss is going to go golfing this weekend. And here are some prior cases in which I've observed whether my boss has gone golfing. So we have the weather outlook, rainy, overcast, sunny. We have temperatures, hot, mild, cool. Humidity levels, normal or high humidity. Whether or not it's windy, it's really windy outside. And did my boss go golfing? So I have 14 total inputs. So 14 different occurrences, different occasions in which I have observed whether my boss has gone golfing. And we want to solve the problem of should we go play golf with the boss because we want to try to get that promotion? There are 3 steps to this process. The first step, I want to find what is called the prior probability. What is the probability my boss is going to go out and play golf? The second thing that we need to figure out is, given each one of those inputs, that outlook, the temperature, the humidity, the wind level, what is the probability, given this, that we will go golfing? Finally, take the new data that we've learned, plug it into our formula, get our answers. So let's start with the priors. In 9 out of the 14 cases, the boss went golfing. In 5 cases, the boss did not go golfing. So that is our P of B. Yes is 9 out of 14. No is 5 out of 14. Our outlooks. On 9 of the 14 cases, boss went golfing. Temperature. Actually, you know what? I have a typo here because outlook was the sunny, mild, overcast. So if I come back here, rainy, sunny, overcast, I need to fix that slide. But basically, it's figuring out the likelihood of each one of those. With temperature, we can see it clearly. Hot, mild, and cool. Well, on hot days, we went golfing 2 out of 4 times. On cool days, we went golfing 3 out of 4 times. So we have the probability that yes, we're going to go golfing. So P of yes is kind of interesting here because you can see 2 out of 9, 4 out of 9, 3 out of 9. So these things have to add up to 9. These things add up to 5 because we went golfing 9 times. We did not go golfing 5 times. And in the cases where we went golfing, it was a hot day 2 out of 9 times. So the probability given that we go golfing that the weather is hot is 2 out of 9. That's P of A. P of A given B. So you can see the math starting to come together. With humidity, we have probabilities again, yes or no. And all of these sum up to the same numbers, 9 and 5, but the breakouts are a little different for each. So we're going to try a new day. We're going to predict whether or not the boss will go golfing. We look outside, look at the weather forecast. It's a sunny day. It's a hot day. It's normal levels of humidity, though, and it's not that windy. So what we're going to do is predict, will the boss go golfing? Yes or no? And we're going to calculate all of the possible classes. And by classes, well, what I mean are yes and no. So we have a 2-class problem. Yes, you're going to go golfing. No, you're not going to go golfing. And I need to calculate those independently. The probability of yes is this formula. So given that we're going to go golfing, what is the likelihood that the outlook is sunny? Given that we're going golfing, what is the outlook that, or likelihood that the temperature is hot? Given going golfing, normal humidity. Given that we're going golfing, no wind. And then multiply that by the probability that we go golfing. Do the same thing for the no's. Now, I mentioned that getting P of A is really difficult. But what's interesting here is T is today. So the likelihood that all of these 4 will be true, that it will be a sunny day, a hot day, a normal humidity, and a false wind factor. I don't know the probability of that. I don't know the probability that all of these things are true. But P of y given t and P of n given t both have the same common denominator. So what that means is when I compare these two, I can cancel that common denominator out. I can effectively avoid P of A. I don't have to calculate it, I just factor it out. That's really good for us because the answer will still be ordinally correct, meaning that I don't need to know the exact probability that we will go golfing given the current conditions. I just need to know if yes is more likely than no. And that's what we're going to learn. So you put this in numbers. 2 out of 9, so that's the likelihood of going golfing given that the conditions are sunny. 2 out of 9, the likelihood that we are going golfing given that the temperature is hot. 6 out of 9, we're going golfing given that the humidity is normal. 6 out of 9, we're going golfing given the wind factor is false, it's not windy. And 9 out of 14, boss's general likelihood to go golfing. So we multiply all of those together and we get this number, 0.0141. The probability of not playing golf. Multiply those numbers, it's 0.0068. Now, remember, technically, there's a P of A down here. So we actually have like divided by some variable x. But because I'm comparing this versus this, the x's will cancel out. So I don't even have to think about them. I just have to compare the numerators because the denominator is equal. And I know this guy is bigger than this guy, so therefore this is more likely to happen. So therefore we are going to predict, yes, boss will go golfing. If there are any questions about this, by the way, please pop them into chat if I'm speaking too quickly, if I'm going through concepts too quickly, if you'd like clarification on anything, let me know in chat, and I should be able to see it, hopefully. In the meantime, I'm going to try to solve another problem, a natural language problem. So naive Bayes, one of the most common uses for it historically has been in spam filters. If you have Gmail, you have that spam box. And one of the most successful early algorithms was naive Bayes. It wasn't perfect. You would get some non-spam messages that get put in the spam box. You would still get some spam messages, but it was generally pretty good overall. They've since changed and used other algorithms, but they started with naive Bayes because it was fast, it was efficient, and it worked pretty well. We're going to see an example of using natural language to classify something and solve it by hand. In this case, I have tags of text. I have little bits of text, and I want to describe whether they reference an article in a business section or if they reference something related to baseball. And so each of these snippets will correspond to one of the two. What we can see is that I have some business, I have some baseball. For this case, I've only got a few scenarios, and it's split 50-50. What I'd like to do is take this text throughout the runner and understand whether it is a baseball term or a business term. If you're familiar with baseball, you will realize very easily this is a baseball term. If you have never heard of anything related to baseball, you may not know that this is a baseball term. The computer doesn't know, so we need to teach it. Here's how we're going to teach it. We're going to find the probability of a phrase being baseball or business. That is our prior probability. We're going to find the probability of the words in the phrase being business or baseball. And then we're going to plug those values from the new data into our formula to give us the proper calculation. So calculating the prior probability is really easy. As I mentioned, there are 3 baseball terms, there are 3 business terms. So for both of them, it's 50-50. Now, our features are the actual words. I don't have anything other than the words themselves. In my early motivating scenario where I was talking about classifying an article as whether or not, as if it belongs in the weather section, I purposefully created some features: author name, number of words, number of paragraphs. It turns out that when you're dealing with text, most often that metadata around your text is less important than the text itself, than the words used in the text. And we're going to dig into here and classify based off of the specific words. So let's calculate the probability, given that this is baseball, of the word through appearing. That means we count how many times the word through appears in the baseball texts and divide by the number of words in the baseball texts. Well, if I hop back a couple of slides to where those are, I can see the word through is right here. So through a no-hitter. And by the way, if you looked at a count of all of the words here, there are 18 total words. What I should point out is the word out appears twice. We count it twice. So we count it every time it shows up. So 1 out of 18 words is through. I mentioned out and out. The word the, if I look in these texts, the third word is the. It doesn't actually show up in this text. And this is where dealing with natural language can run into a major problem, because as soon as I get to the, I have a 0 out of 18. So I'm multiplying the probabilities together, and if I have 0 out of 18, therefore the probability is 0%. Well, if I do the same thing with business, the word through doesn't appear once. So business is 0%, baseball is 0%. Basically, our model is saying it's not anything. I can't classify it. But the problem is you're liable to see new words. You're liable to see things that you haven't seen before, and your model shouldn't immediately fail as a result of that. People misspell things. People use different forms. They use different conjugations. They might throw in an exotic word. Your model shouldn't fall apart just because of that. We should be able to adapt to that scenario. And to do that, there is a concept called Laplace smoothing. The idea is we add 1 to each count so that it is never 0. So we add 1 to the numerator, and we add n, which is the number of unique words, to the denominator. There are 29 unique words in the entire data set, and I've listed them all out here. So what we'll do is, for the word through, we were at 1 out of 18. And I'm going to add 1 out of 29. So just add the number 1. No matter how many times through appears, we're going to add 1 more to it. And we're going to add the total number of words, of unique words. So out, 2 out of 18. So we had that. We're going to add 1 to the numerator. We're going to add 29 to the denominator. So all of our baseball denominators will be 18 plus 29, 47. And here we'll have 2 out of 47, 3 out of 47, 1 out of 47, 1 out of 47. For business, we have 43 words. The word through doesn't show up, but we add the 1 to it so that we don't get a 0 probability. So it'll be 1 out of 43, 1 out of 43, 2 out of 43, 1 out of 43. One thing I want to point out here, the word runner. I have 0 for baseball, but I had a phrase that said runners on second and third with nobody out. Well, this is one of those tricky bits. The word runner is not the same as the word runners. They are, in fact, different words. So as a result, we can't treat them as the same. Different conjugations, different forms of a word are considered to be different for naive Bayes. And therefore, runner is 0. So let's do our probabilities. Probability, given the term throughout the runner, that this is a baseball concept, is the probability of each of those words being baseball concepts multiplied by the probability that you'll have a baseball term as opposed to a business term. So basically it ends up being this really small number, 6.15 times 10 to the negative 7th. Oh, there we go. And the likelihood that this is a business category given the term throughout the runner is 2.93 times 10 to the negative 7th. So the baseball term is more likely to happen than the business term. And it looks like it's about twice as likely. So the probability that's a baseball term is about 67%. The probability it's a business term about 33%. But what's important is the baseball number is larger, and therefore baseball is the best category for our phrase. Now, there are a few ways that we can make natural language processing results more effective for us. The first one is to remove stop words. Stop words are words that appear in every document. They appear everywhere, and they don't have a good direct meaning. By direct meaning, what I mean by this is they don't really modify the text. A, the, on, of. Yes, prepositions are important. Articles are important, direct or indirect. But if I have a direct article, if I have the word the, it's not going to change the category of my text because the word the will appear in nearly 100% of all texts. We can do something called limitizing words. So that's where we group together inflections of the same word. That's how we would get runner and runners. We would knock off the both of those and probably just say run and have both of them show up as the same. We can use n-grams. So an n-gram is a fancy term for a sequence of n number of words. Like if I say I want 3 grams, using the term throughout the runner, the first 3 gram would be the term throughout the, and the second term would be out the runner. The benefit of n-grams is that words will modify each other based on their nearness, especially in languages like English, where we put the modifiers very close to the affected words. So usually we'll put adjectives very close to nouns. We'll put verbs very close to nouns. This is in relation to a language like German, where you'll have the acting verb quite often at the end of the sentence or at the end of the clause, which could be quite a distance from the affected noun or the affected object. So we can use n-grams to get bundles of words and likely make the result even more effective. There's a final concept called TF-IDF, term frequency, inverse document frequency. And this is where we look at how frequently a word appears in documents, and we actually penalize the words that appear most frequently. That's sort of like a step on the way to stop words. So if I have the term the, again, the appears in pretty much every document, it is not a meaningful term for classification. Whereas if I have a very technical term that is very specific to the concept, like in baseball, if we talk about say salary arbitration, if we talk about rawhide, if we talk about something that is going to be much more frequently used in baseball terms and much less frequently used in general business terms, that will have a higher frequency, that will have a higher value. It'll have lower frequency, appears less often, but much more indicative of being a specific category. So there was a lot in there for natural language. And again, if you have questions, please do feel free, put them in chat. I'm happy to go over this in some more detail. What I'd like to do now that I have a general understanding of how this works and that we've solved a couple of these problems by hand, I want to show you how to do this without having to calculate it by hand. And we'll start with R. We'll start with the relatively simple feature solution and using a package called Naive Baze. This is a fast solver for Naive Baze. It's got some built-in functionality that makes it easy for us to work with. And I'm going to use the infamous IRIS dataset. If you've done anything with data science, you've seen IRIS far too many times. But it's a really good one for classification because it's small, it's well known, and it has interesting results. So I have here the code that we're going to use. I'm actually going to blitz through this code now, and then we'll see it in action. So we install the package. We install the Naive Baze package and also the Caret package. Caret is going to allow us to work with oh, sorry, I'm reading the question. So Eliza, the approach of ignoring the denominator is okay also for multi-class classification as far as we compare all the categories. Is that correct? Yes, that is absolutely correct. Basically, you're doing a one versus all in that case. So what we're looking at is all of the numerators. If you have 100 classes, they'll all have the same denominator. So as you're comparing each one of them to each other, they'll all have the same denominator. So yes, we can safely ignore it. This means that we won't necessarily know the true probability. You can kind of do the math and get to the true probability, but we don't care about the true probability. We really just care about which one of these classes has the highest probability, regardless of what that number actually is. So the answer is yes. Okay, Caret allows us to train data, like split out data between training and test data sets. It allows us to analyze results. It's a helper package for data scientists. We're going to split out our data into first we're going to randomize the data. So I'm basically shuffling the data a couple of times. We're going to split out data into training and test. 80% of the data will be trained, the remaining 20% will be in test. We'll use the Naive Bayes function to try to identify the species. So in the IRIS data set, there are a few inputs and there's a species. There were 3 species of irises that the professor who put together this data set looked at. And based on the length of the sepal and the width of the sepal and the length of the petal and the width of the petal, we have a species. And so we're going to try to predict that species given petal and sepal lengths and widths. Then we're going to actually generate our predictions and bind that as a new column to the result. So in T-SQL terms, think of it as we have our input data set, we have a table that has our input data, we have a table that has our predictions, and we're going to join those together. So let's look at that in a demo. Here's our first demo. We're going to use a Jupyter notebook, and I've already pre-run all of this, so it should be fast. We'll load up those 2 packages as mentioned. Here's the IRIS data set. So we have sepal and petal, length and width. They're just different parts of the flower that specify, and we specify the width and length in millimeters and the species. So there are 3 species of iris in this data set: setosa, virginica, and versicolor. After that, I'm going to shuffle my data and break it out into training and test. We'll run this Naive Bayes function against the data set, and I'd like to plot the data. So here's what we have. This is sepal length. And what we see with sepal length is that for our 3 flowers, the Virginica sepal length is in blue, versicolor green, setosa red. And what we're looking for is the amount of overlap. So with setosa, based on sepal length, if your sepal length is within, actually, let's say about this range or so, it's almost definitely setosa. If it's past about that point, it's almost definitely Virginica. In the middle, it gets a little mushy. So if your sepal length is, say, somewhere right about there, if I draw a line straight up, we can see there is a probability that it would be all 3 flowers. So sepal length isn't a great separator for us. Ideally, what we want to find is 3 completely independent humps. And if we find 3 completely independent humps, we'll know this is this is a good way to split the data out. If I come down here to sepal width, it's even worse. There's a huge amount of overlap between the 3. So we're probably not even going to look at sepal width. It's just too messy. Petal length. Now we're onto something. With petal length, if it's below about that point, it is setosa. And for Virginica versus versicolor, if it's below about this point, it's almost definitely versicolor, and if it's above about, say, there, it's almost definitely Virginica. And we just have to worry about in this range because it could be both. Similarly with petal width. So if we have a very narrow petal width, it's setosa. If we have a moderate petal width, it's probably versicolor, and a wide petal width, probably Virginica. And we can look at each one of those independently and get the cross probability of those 4 to give us predictions. So once we have those predictions, we can create what is called a confusion matrix. This is, of our 30 tests, we predicted setosa. How frequently was setosa correct? So 11 out of 11 times. Great. We predicted versicolor. What was the reality? Well, 9 out of 9 times when we predicted versicolor, it was versicolor. When we predicted Virginica, 8 out of 10 times it was Virginica, but actually in 2 cases it was versicolor. So we can collect accuracy. Accuracy is the probability of basically summing up these 3 boxes divided by the whole amount. So it's 28 out of 30, or 93%. We can also get other values. So here we have positive predictive value, negative predictive value. We have sensitivity and specificity. And I've given you some definitions of positive and negative predictive value up here, because those are quite useful for understanding how well we classify within a specific class. There are some key cases where accuracy is not a good enough answer for us, and positive and negative predictive value are very helpful in that regard, because I'm able to say, for example, positive predictive value. If I predicted versicolor, so I predicted versicolor, what is the probability that this was in fact versicolor? And in this case, it was 9 out of 9. If I predicted Virginica, what was the probability that it really was Virginica? Well, that's 8 out of 10. The numbers I have up above are a little different. That was from a prior run. So they may shuffle, they may change just a little bit based on versions of R, versions of when you run the code. But anyhow, we can see Virginica, 80% positive predictive value. I predicted Virginica 80% of the time it was Virginica. Negative predictive value. I said this is, say, not versicolor. If I said this is not versicolor, what is the probability that I am correct? So 11 out of 11 plus 8 out of 10. So in other words, 19 out of 21 times, I was correct. That's roughly 90%. Now let's talk about natural language processing. Here's where it gets kind of fun, because doing a real natural language processing problem is quite mentally and computationally intensive. We did a really simple problem by hand, but once you start talking about lemmas and stop words and other implementations, there's a lot of effort involved if you had to do it manually. The naive Bayes package does handle natural language processing, so we can work with that approach as well. But we're going to perform some data cleanup operations to make our results better. And I have a walkthrough of here. I'm actually, instead of walking through the code in this segment, I'm going to take us to the demo, and I'll walk through the code in there. So let's go look at that demo now. All right. So I'm going to load up the naive Bayes package and a few other things. One thing I want to point out is that I'm using a specific version of naive Bayes because later versions changed some functionality that breaks this demo. So I'm kind of sticking with an older version instead of rewriting the version. I'll probably rewrite this at some point to use the latest version of naive Bayes. But yeah, they changed some behavior that made it really difficult to work with for natural language processing when you have different input sets. So our data set is 2,000 movie reviews. And each movie review is classified as either a positive review or a negative review. And we have the text of the review. And some of these texts can be really long. So what I want to do, just like before, is shuffle up my data. And I'm going to set class of positive or negative as a factor because it's either going to be a positive or a negative. It's not really text. What I want to do next is build what is called a corpus. Corpus is essentially the full set of data. Here is all of your documents. We have 2,000 documents, 2,000 reviews. Then I'd like to apply some rules, and I'll use the text miner package to perform operations. First, let's lowercase all of the words. Case sensitivity can matter in natural language processing, but most of the time, in a language like English, most of the time, casing capitalization doesn't matter. So I don't want the with a capital T and the with a lowercase t to be considered two separate words. Therefore, everything's going lowercase. I'm removing punctuation. I'm removing numbers. I'm removing stop words. And there's a built-in dictionary for removing English language stop words that includes prepositions, articles, and extremely common words. I'm also removing white space. Anybody had a tab stop in there? They had a new line. They had several spaces. These are things which I want to take out to simplify the problem as much as possible. So I've applied those rules. So we're doing it right now. There we go. And it does note that, hey, you've dropped some documents. That's okay. If we lose a few documents that were messed up, I'm not too concerned. I still have enough data. Now, the next trick here is to convert words to features. Each word is a feature. We're using a technique called bag of words. There are other techniques as well that are generally better than bag of words, but bag of words essentially means take the unique set of terms. So every word that appears, and we're going to use all of those as our input, the unique set. So let's create a document term matrix. And here's a quick look at what we get out. So we have each word believability, biased, big, bill, bit. And we have the number of times that word appears in this document. So in document 40, the word bit appears 3 times. The word bit does not appear in document 41, and so on. So we have this matrix. Then I can split this out into training and test data. So I'm going to take the first 1,500 rows, that will be training, the last 500 rows for test. We're going to create the document term matrices. We're going to get those out, split them into training and test, and our cleaned corpus results into training and test. Inside training, we have 38,957 unique terms. But a lot of these terms only appear once. And if you only appear once, the likelihood that it'll show up again is pretty low. When you're using TF-IDF, like I mentioned before, that's actually a good thing. This is a unique term. If you see it again, it's very likely to be associated with whatever class this thing had. But if you have a large number of terms, you may have millions or tens of millions of terms, and you have tens of millions of documents, and that becomes a massive memory problem. So if you have memory concerns, we can limit the input set to terms that show up more commonly. And by common, what I'm going to say is you were in 5 separate documents. There were 12,000 terms that showed up at least 5 separate times. And so I'm going to basically take out any words that don't appear in this 12,000 word set to reduce the amount of memory required. Then I'll create a quick little function that basically says, I don't care how many times you showed up in here. The fact that you showed up is the only thing I care about. So take any number that is not a 1, make it a 1. Keep zeros. So if it's a 0, keep it at 0. If it's greater than or equal to 1, make it a 1. That's what this function is currently doing. And it's also creating a factor, basically yes or no. Yes, this word showed up. No, this word did not show up. Now that it's done with that, we can pass this into our naive Bayes classifier. And I've turned on Laplace smoothing because there may be new words in the test data set that did not appear in the training data set. That was our scenario, like the throughout the runners, where the word the didn't appear in a baseball scenario. So I want to make sure that we don't end up with a case where everything's 0 probability. So we get our results. Confusion matrix. Basically, was this a negative reference? So in other words, reference data, was this a negative review? Did we predict it to be a negative review? 219 times when we predicted negative review, it was in fact negative. 73 times when we predicted negative, it was positive. 31 times when we predicted positive, it was actually negative. 177 times we predicted it was a positive review, it was a positive review. That gives us an accuracy of about 79%. So even if you didn't know a word of the language itself, assuming that you knew 0 English, or if we changed this to, say, Mandarin Chinese, or if we changed it to Indonesian, I could get a data set in which I can't understand anything in that data set, but the computer can still classify based on the labels, based on that positive and negative. We get down here to other values that become important: sensitivity, specificity. We talked about positive and negative predictive value. Basically, if I predict this thing, what is the likelihood that it really is that thing? If I come up here, sensitivity, when we consider something as, when we capture that the event is positive. So this is positive. What is the likelihood that we're going to find it positive? So in this case, it's 177 divided by the quantity 177 plus 73. And so that is our sensitivity. Specificity, when we say it's a negative, what is the likelihood it's a negative? So if I come down here, specificity, 87%, which is 219 divided by the quantity 219 plus 31. Sensitivity, 177 divided by the quantity 177 plus 73, which is about 71%. And these values can combine with accuracy to give you a feeling for how good this model is. In short, it's not a bad model. It's not a perfect model for sure, but it's an okay model. And it's definitely a reasonable start. From there, we can apply other techniques. We could try using word2vec to vectorize instead of bag of words. We could try using online passive-aggressive algorithms or a neural network to try to classify, to eke out more gains. But we can say, here is our baseline. We have at the very least a model that is about 80% accurate, 70% sensitive, and 87% specific. And if that's good enough to go to production with, I can give you those results very quickly. So that's the real benefit of naive Bayes. Within a few minutes of me just chatting, we have an answer that is at least a first approximation of how well we can do. So what do we do next? Well, after you've looked at naive Bayes, there are some other algorithms that can be interesting. Logistic regression is a really good one if you have a two-class problem, a yes-no, baseball versus business. If you have multi-class problems, logistic regression is not going to work so well. There's an approach where you can do it. It's one versus all, but you might switch to something like decision trees or random forests, maybe gradient boosted trees. I mentioned online passive-aggressive algorithms. This is a really interesting approach to solving the problem. It actually works extremely well in my experience, but it can be memory intensive. You can use a neural network. Depending on your case, it might be a multi-layer perceptron. You could use a convolutional neural network especially if you're trying to classify images, or you might use a recurrent neural network. And support vector machines have been around for a few decades. Historically, it's been a very memory and compute intensive algorithm. Prior to neural networks taking over the scene, SVMs were generally one of the most popular algorithms for this sort of problem. But you can see there are a lot of other algorithms beyond this that you can try out, and many of them will take more time, more effort to get to. So you could use naive Bayes as how well do we think we can do, and then use one of these to try to get further. And it may turn out naive Bayes actually does work the best in your scenario, in which case you just stick with it. So wrapping up, naive Bayes is a class of algorithms simple to understand, reasonably accurate, and that's a good starting point. There are superior algorithms for specific problems, and based on your scenario, you might try one of those out. But if you start with naive Bayes, it at least gives you an idea, is this problem solvable? And if it is solvable, what's my baseline? What should I expect? And how can I improve it? If you'd like to learn more, if you want to grab the slides, if you want to grab the notes, demos, links to additional resources, that is at csmore.info/on/naive Bayes. If you have any questions at all, please do feel free to reach out to me. There's my email address and my Twitter handle on the screen. And if you have questions that would involve some more detailed consulting work, you can check that out. But we've got 5 minutes, it looks like. So if there are any questions for anybody, please let me know.
Thank you very much for your session. You have already answered the question during the session. There isn't questions for you.
Oh, Eliza has a question. How is this algorithm related to explainability? So that's a good one. Basically, This is, I would consider, extremely easily explainable because you can talk through the math behind this, and you have the independent probabilities of each of those items. So if I go back to how we calculated the example of golfing, we can say here are the different weights of each, and each input is factored. They all have essentially the same value, the same, say, consideration in the model. So it's very explainable because I could actually show you the numbers that derive how we get here, versus something like a complex neural network that's, say, multi-layered, where it gets a lot trickier to explain how I use a particular input and how it becomes an output. With naive Bayes, it's extremely straightforward. And explainability can be an important factor as part of, say, responsible AI, or as part of working in a regulated industry where I need to be able to show that I'm not using certain inputs, I'm not using certain factors for prediction. If features are highly correlated, this would impact negatively on the naive Bayes performance in terms of accuracy, or is a good baseline also in this case? So that's where things get really interesting about this, because logically, yes, if you have high correlation between features, you would expect naive Bayes to do a really bad job. But the interesting thing is that in practice, it actually still does a pretty good job. There are scenarios in which it can perform poorly as a result of that cross variance, that covariance. But in most scenarios, even where you have moderate covariance, ignoring that covariance doesn't affect it as much as you'd think. So the short answer form of that is, yes, it can, but it quite often doesn't.
Thank you. Thank you for the answer.
All right. Thank you, everybody. Appreciate the questions. Appreciate your time today. Have a wonderful rest of your day.